let me define something definition. Some definition of GCD. You know already the definition of GC, greatest common divisor. We already know. Suppose RBA. Now I'm defining in arbitrary ring. What actually the GCD is actually, because we have already defined Euclidean algorithm, Euclidean domain. Now we can define about the GCD. Okay. So let R be a commutative ring. Let R be a commutative ring. And A comma B inside this ring R, suppose. Okay, and B is a non-zero element, suppose. Okay, A is said to be a multiple of B. This A is said to be a multiple of B if there exists an element X is in R on the ring R with A can be written as some Bx, B into X. And we say B divides A, or B is a divisor of A. Oh, that's fine. B divides A. We write this B divides A in this format. Okay. And the second is a greatest common divisor of GCD. A greatest greatest common divisor of A and B. What are the elements of R? Okay, is a non-zero element D such that first D divides A and D divides B, and the second is if there is another D dash which divides A and another D dash which divides B, then D dash divides D. Then we say D is a greatest common divisor. Okay, we have already seen for this, and in the case of ring of integer Z, right? So, and you should have to recall one thing more, that is, suppose you have suppose you have D is dividing A. That means that ideal generated by A is contained in ideal generated by D. Also, if this happens, this side is also true. Why this is true? Suppose D divides A. This implies that A equals to some dP, which is inside ideal generated by D. This implies that this ideal generated by A is contained in ideal generated by D, and the reverse side is this side forward, and the reverse side is, suppose A is an element of ideal generated by D. This implies that A equals to dk. This implies that D divides A. A simple observation or simple manipulation. This is D divides A. Simple manipulation. Just now some another definition. Just these are some definition. What is, now I will define something. Suppose let R be a ring. Sorry, R be an integral domain. You should integral domain. R be an integral domain. So now you can define something is called irreducible element. Suppose R be an element of R, an arbitrary element of R, which is non-zero. R is non-zero element of R and non-unit then R is called irreducible. Something has to be irreducible element. This is called irreducible element in R if whenever R equal to AB with A comma B is in R, at least one of A, at least one of A or B must be a unit. Suppose, see, if you have any R element here, R, this R, if you can write R equal to some A into B, then either A is a unit or B is a unit. Then we say this R is a irreducible element, that this R cannot be reduced. Okay, R equal to some either unit time A or some unit B times unit, A times unit. Okay, A times unit or unit times B. Okay, that means R cannot be reduced, otherwise it called reducible. Otherwise we call R is reducible element. Okay, and the second definition is what is called a prime element. In the non-zero element, a non-zero element P inside the ring R is called prime element. Actually, it's called prime element. Prime element in R if the ideal generated by this P is a prime ideal. In other words, a non-zero element P is prime. In other words, a non-zero element P is a prime element if it is not a unit. First of all, it's not a unit, and whenever P divides AB for any A comma B inside the ring R, then either P divides A or P divides B. Then we say this P should to be a prime element. Okay, otherwise, okay, prime element, the definition of prime element and irreducible element is clear, right? So now what one more, this is called associate. When do we say two elements are associate? Two element A and B of R, two elements A and B of R is said to be associate to each other if A and B are differ by a unit, that is if you have any A at unit time B, where U is unit, or B equal to some U dash time A, U dash is a unit. Okay, then we say that two elements A and B, this A and this B, and said to be associate of each other. Now I am going to write a proposition that in a PID, the definitions are clear, right? The definitions are clear. Suppose I have defined irreducible element. What is irreducible element? Irreducible, suppose you can write an element R equals to AB, then either A is a unit or B is a unit. Okay, after that, what is called a prime element? Either is called either P is called prime if ideal generated by P is a prime ideal, or in other words, if P divides AB, two elements AB, that means AB is the product of AB, then either P divides A or P divides B. This is the as usual definition in case of Z. And two element A and B are said to be associate of each other if they differ by a unit. Okay, associate, this is called associate of each other. A, that means A equal to some unit time B, or B equal to some unit time A. That's the idea. So now I am defining something, a proposition here in a PID, that means principal ideal domain, where every ideal is generated by single element. In a PID, every non-zero, this is important, okay, prime ideal is maximal, and conversely, that means every maximal ideal is prime. See, every maximal ideal is prime, this is always true. If you have any maximal ideal, it should be prime. So this case, converse case is obvious, quite obvious. It's just simple manipulation. What is, if it is a prime ideal, then how can I show this ideal is going to be maximal ideal? So suppose let capital P is ideal generated by small p be a non-zero prime ideal. Why I am denoting this capital P to be generated by single small p? Because you are in a PID, so it will be generated by some single element. Suppose the single element is small p. Okay, a non-zero prime ideal. And now, and let this M is generated by some single M be any ideal that contains P. What is my P actually? P generated by P. That is, your P ideal generated by P is contained in ideal generated by M. That's, so this implies that P equal to some M times R for some R is in R. This implies that P equal to MR is a member of this P, which is ideal generated by P. That means MR is a member of P. Since P is a prime ideal, now I will use the fact that since P is prime ideal, this implies MR actually P. MR inside P implies that either M is in P or R is in P. So now case 1, suppose M inside P, or suppose R inside P. Suppose R inside P. Suppose, and P generated by P. This implies that R equals to some pk for some k inside the ring R. Okay. Also you will have this P equal to mr, then R equals to mr k, since P equal to mr from here. Okay, now what you can say, this P into that P, okay, R okay, now this will not work, I guess. What I am actually going to do is will not what you can do, you have this P, let's keep it aside, let's keep it aside and do as usual thing. You have P, what is P? P equal to mr. Now you put the value of R here, m into pk from here. This means that P into 1 minus mk is 0. This implies P is non-zero. This implies mk equal to 1. This implies that m is a unit. If m is a unit, that means m is actually, if an ideal contains a unit, that means that ideal generated by m is equals to the entire m, which is actually R. Okay. And if m is in P, which is ideal generated by P, this implies that the ideal generated by m is actually ideal generated by P. Why? See, m is here, okay, already here, and you also have, see, m is in P and P is actually ideal, that means the ideal generated by m is a subset of ideal generated by P. But you already have ideal generated by P is contained in ideal generated by m. These two together implies that the ideal generated by m is actually ideal generated by P. That means every prime ideal is going to be a maximum ideal in a PID, right? This is the definition of maximum ideal. If it is not there, then it is the entire ring. If it is, and either otherwise, this P is actually the maximal ideal. The ideal generated by P is actually the maximal ideal. Okay, I have started with a prime ideal P, and I am showing that this is the maximal ideal. Otherwise, it is entire ring. So every ideal, every non-zero prime ideal is maximal, and and by definition every maximal ideal is prime. There is nothing to prove about the maximal ideal here, right? So I think the proof is clear, right? Now let me come to some examples. The most important thing is example, otherwise so okay, so what kind of example I can consider? Okay, before example I want to give you something. Before example, we'll come to example within a minute. Okay, within a minute. So now I am giving you some another proposition. Suppose if R a commutative ring with unit CRU, and this R polynomial ring over this R is a PID, that means principal ideal domain. So this implies that R is a field. How do we know that this is going to be a field? Proof. Do you know this is a field? So this is a very easy obvious thing to check. you just define a map from this Rx to R. What is any Px, any polynomial you can talk here is you go the evaluation at 0, P at 0. This will be member, and this is a onto ring homomorphism, surjective ring homomorphism, and also the kernel of F is actually all those polynomial Px such that P of X is P of 0 is 0. The kernel is all those okay, and this is going to be the only the P0 means the constant term is 0 here. So this means that this is ideal generated by X. That means by first isomorphism what you can say, Rx by ideal generated by X is isomorphic to this R, but this R is an integral domain. R is an integral domain, and okay, R is an integral domain. I have not told. Okay, so it is following from here because Rx is a PID. That means Rx is in fact ID. That means R is an integral domain. In fact, R is an integral domain. So R is an integral domain. So this is an integral domain. So this means that the ideal generated by X is prime. This means that ideal generated by X is maximal, because if Rx R mod I is integral domain, this implies that I is prime. We know that already. So Rx by ideal generated by X is isomorphic to R, which is an integral domain. This implies that X is a prime ideal. This means the ideal generated by X is a maximal ideal, because you are in a PID. So every maximal ideal is going to be prime. Every prime ideal is going to be maximal ideal, and conversely. So this means that is a maximal ideal. This means that Rx by ideal generated by X is a field. Rx by ideal generated by X, which is actually isomorphic to R, is a field. Okay, I think it is clear because I have just defined a map, and it is onto surjective. Onto-ness is easy. You take any polynomial, you take any number, you can make a polynomial. So this is onto. I don't even care about, and this is Rx by ideal generated by X. No, Rx by ideal generated by okay. And I don't bother about whether it is 1 or not. I just want to make this why this is an integral domain. R is an integral domain because Rx is a PID. That means that Rx is a integral domain, in fact, right? This means that R is a integral domain. Rx is an integral domain if and only if R is an integral domain, na? So this is a key point. So this Rx by ideal generated by X is an isomorphic to integral domain. That means this is a prime ideal. This means that this is a maximal ideal because you are in a PID. So this Rx by X is isomorphic to R. This is a field, right? I think I am clear. So now let me so what actually we know that F is a field. This means that F is an Euclidean domain. This means that this F is a principal ideal domain. This implies that this Fx is an Euclidean domain. This implies that this Fx is PID, and this implies that PID, and this implies that this F is a field. Okay, so F is a field. This means that F is an integral domain, Euclidean domain. That means F is a principal ideal. Every Euclidean domain is a principal ideal domain. So if F is a PID, then Fx is a ED. F what X is an ED na, by degree formula. We have already did na, by degree formula, and this implies that Fx is PID, and Fx is PID. This means F is a field. We just now proved this. So I think this much is clear, right? but ZX is not a ED, not a PID. Okay, ZX means it's not ED, not a PID, because if it is not ED then it cannot be PID. Okay, so fx is a field. Effect is a field if and only if fx is a PID. If and only if f is a field, if and only if fx is a ED, Euclidean domain. Okay, so now what you know, that ED, Euclidean domain, is properly contained in PID. What is the example, proper example? Z of one plus square root of minus 19 by 2. This is a ED but not PID. Okay, this is properly contained. That means ED is properly contained here. This is a Euclidean domain but not a PID. Okay, that you know. This is the for properness you can take this as example, right? So now you know that Z is what is Zi, right? The ring of Gaussian integer. What is this? This is A plus some Bi type element, where A and B are from integer. Okay, you know that. If you know that, so you know this is an Euclidean domain in ED. By that, the norm will be norm of A equals to, what is that? What will be the norm? Norm of A plus IB. One element A plus IB type equals to A square plus B square. This norm, this is going to be an ED, because for ED we need just a norm, right? We don't need anything else. Norm of A plus IB equals to X square plus B square. So now I will show something, that suppose you have this Z is a ED. This means that Z is a PID because Z is an ED, right? Now let I be any non-zero ideal of Zi. That will definitely be going to be a principal ideal because you are in a PID. My claim, what is that? Now you can quotient it, Zi by ideal generated by I. You can quotient, right? So what kind of elements are here? That is some A plus IB plus some I type element, where A comma B inside this Z. My claim that Zi is always a finite set. The Zi by ideal generated by I is always finite whenever I is non-zero. So how can you show that? Proof. This kind of question might ask. Okay, this is an important question, that Zi is an infinite, so I is a non-zero ideal. So how can you show that this is going to be a finite set always, or finite is always going to be finite? So I don't say it is a ring or something, but it is always a finite. Okay, finite quantity. So proof is simple. Suppose this ideal is generated by some alpha plus I beta type element, that it will be generated by single element, na? So suppose this I is this. So an element you can take to be from here. Let a plus ib plus I is a member of Zi mod I. Okay, this is one arbitrary I have taken. So I can definitely apply division algorithm because you are in a Euclidean domain. So using division algorithm, what you can say that any a plus ib can be written as some alpha plus I beta time q1 plus iq2 plus r1 plus ir2, with r1 plus ir2 equals to 0 or norm of this is less than norm of alpha plus I beta. Okay, norm of r1 plus ir2 is less than norm of alpha plus I beta. Okay, so what you can do now, because see you are having with this, so a, what you can say more, a plus ib, you can add I here. So similarly I will add a plus alpha plus I beta into q1 plus iq2 plus r1 plus ir2 plus I. But your alpha plus I beta is an element of I, so it will be definitely a member of I. This is also element of I. This implies that a plus ib plus I is equals to r1, because this will definitely dominate by here, r1 plus ir2 r1 plus ir2 plus I. That much it is okay, right? With what you have, r1 plus ir2 equal to 0 or norm of r1 plus ir2 is less than norm of alpha plus I beta, is not it? So norm of this implies that r1 plus ir2 is 0 or norm of alpha plus beta means alpha square, r1 square plus r2 square is less than alpha square plus beta square, is not it? So what are the choices for r1 and r2? See, this quantity is less than this. This actually implies that either this or r1 square is less than alpha square plus beta square, or r2 square is less than alpha square plus beta square. That means you have choices for r1. See, this element is totally depending on this element, but your choices for r1 and r2 are finite, because see, r1 square is less than equals to alpha square plus beta square, and alpha beta is a member of this ring. So this choice is actually your finite. That means your a plus ib has to be a finite number of choice, because you have a finite choice, right? You have to be, this a plus ib has to have a finite number of quantity, because this r1 is totally depending on here also, and this r2 is totally, because there are only finitely number of solution you can have at most. So this means that Zi by ideal generated by I, any ideal is finite always. Okay, it is always. So let me give you a simple example. What are the examples I can consider? Suppose Zi by ideal generated by 2 plus 3i. This is an ideal, this is a non-zero ideal. What are the elements here? This is a plus ib plus ideal generated by 2 plus 3i, a comma b inside this Z. this actually this ring is this. So a plus ib can be written as ideal generated by 2 plus 3i plus r1 plus r2 with r1 plus r2, sorry, ir2 is equal to 0, or r1 square plus r2 square is less than 2 square plus 3 square. This means that r1 square plus r2 square should be less than 13. Okay, so now you can choice for r1 and r2. That will give you the total number of choices, because okay, and this is your I. Okay, so either r1 r2 equal to 0. If you take r1 r2 to be 0 0, then it is also this zi by ideal generated by what is your I. Actually this is your I is going to be, suppose r1 r2 is 0. This is also a solution, right? This is also a solution, so you cannot take such a thing. So this is you can take this easily, right? I suppose r1 and r2 value, so see r1 and r2 will satisfy 1 and -1 -1 definitely satisfy. That means you can take to be 1 plus I, -1 plus I, 2 plus I, it will also satisfy, -2 plus I will also satisfy, 3 plus I will also satisfy, 3 plus I also satisfy, I plus I will also satisfy, -I plus I will also satisfy. That is this, there are finite number of choice. It will definitely stop somewhere. So this implies that this is going to be a finite, right? Now some other example you can take. So I will giving some question 3 in z of square root of -5 is prime or irreducible. What do you think? What do you think? This 3 inside is prime or irreducible, or prime irreducible both, or neither prime nor irreducible? What do you think? So suppose, what is the solution? 3 can be written as sum a plus square root of -5 into b into c plus square root of -5 into d, suppose. So norm of 3, you just apply norm of a plus square root of -5 into b, norm of c plus square root of -5 into d. This is implies that 9, this is 9, this is equals to a square plus 5b square, c square plus 5d square. This implies that this element is in z, this element is in z, so and together multiply with, so a square plus 5b square equal to 1 or 3 or 9. If a square plus 5b square equal to 1, this implies that a and b are unit, because the norm is 1. This implies that the element should be a and not a and b. It's called a plus ib. A plus square root of -5 into b is unit. The norm is 1 if and only if the element is unit. Okay, and if suppose a square plus 5b square equal to 3, this implies that no solution. So we cannot have any choice here. And if a square plus 5b square equals to 9, this implies that c plus id is unit. C plus square root of -5 into d is unit. So this implies that 3 is an irreducible element. Okay, now what about prime? What do you think about the prime? Is it prime? What do you think about the prime? Is it prime? what about prime? So for prime we have to check whether it divides. If AB divides, then either A divides or B divides. That's the idea. So 1 plus square root of minus 5 into 1 minus square root of minus 5, this is actually 1 plus 5, which is actually 6. See, 3 divides 6, or 3 divides 1 plus square root of minus 5, 1 minus square root of minus 5, same. So does this imply that 3 divides 1 plus square root of minus 5 and or 3 divides, does this actually imply? So if so, if 3 divides, suppose 1 plus square root of minus 5, so square root this implies that 1 plus square root of minus 5, 1 plus square root of minus 5 is equals to 3 times alpha plus I beta. Okay, three times alpha plus I beta. Then you just take the norm. If you take norm here, then it will be 6, and if you take the norm 9 into alpha square plus beta square, so it cannot happen in zx, or if you have to coefficient from in z na. So this implies that 3 does not divide 1 plus square root of minus 5, then it will also does not divide, 3 will not divide 1 minus square root of minus 5. So this 3 is not a prime element. 3 is not a prime element. Okay, so 3 is irreducible, but 3 is not a prime element. Now another question. Suppose you know that z of I, so you know the z of 2i, right? 2i. What is z of 2i? Is of the element a plus 2ib. So that a, b are in z, which actually is subring of zi. My question is 2 inside z of 2i is irreducible? Similar, is 2i inside z of 2i is irreducible? What do you think? See, you have to play with the norm actually. You just have to play with the norm. This is a simple exercise. This is a very easy exercise. I am giving you an idea, a very easy idea actually, what is called solution. So suppose it is 2. Suppose in case of 2, suppose it is irreducible. Suppose whether it is irreducible or reducible, you have to take. Suppose 2 can be written as some a plus 2ib into c plus 2id, isn't it? So you just take norm. This will be 4, and you will have norm here. This is a square plus 4b square and c square plus 4d square. So this is a z, this is a z. So this means that a square plus 4b square has a choice. It can be 1, it can be 2, it can be 4. If it is 1, then this is unit. If it is 4, this is a unit. But if it is 2, then no integer solution will be. If it is 2, there will not be any integer solution for that. But if it is 1, this implies that this element, the element a plus 2ib is a unit. If it is 4, then c plus 2id will be an unit. So 2 is irreducible. Similarly, you do it for 2i. I will not give you much hint because the same idea will work very nicely here. So there is no need to worry too much about. Okay, so what else I can take? Should I have to give some more example? or what do you think? So another question, 2 plus square root of minus 5 is prime or irreducible in z square root of minus 5. What do you think here? The similar thing will work here, similar, exactly similar. You just do as an exercise homework, okay? Because these are some trivial checking, routine checking, okay? So I don't want to waste time over here, right? And I want to finish it as early as possible. So should I define something new? You know, in a PID every irreducible is prime. So no, in an integral domain I will show here. In an integral domain, every prime element is irreducible, but not conversely. But not conversely. Somebody is calling me continuously, I don't know why. In an integral domain, every prime ideal is irreducible but not conversely. But the converse is true whenever you are in a PID, right? So I am giving you the idea of the proof, or I am giving you the proof. Suppose R be an integral domain. I am not writing R be an integral domain, suppose, okay? And I am taking a P inside this R. P is prime element. So this implies that P ideal generated by P is a prime ideal. To show P is irreducible. This P element is irreducible. So let P, that means if you can write P equal to some A times B, then either A is a unit or B is a unit. Let P equal to some, you can retain as some P into A into B, okay? Which is in P, ideal generated by, this implies that either A is in P or B is in P. This implies that A equals to some pk1 or B equals to some pk2 for some k1 k2. I am not writing. So P equal to, we have AB. This implies this equal to, you can write the value of A here. So pk1 into B. This implies that P into 1 minus k1 into B, this is 0. This implies that because B is non-zero here, no sorry, P is non-zero, sorry, here is P here. So P is non-zero, so 1 k1b equal to 1. This means that B is a unit. So similarly, if you put the value of B, then you will get A is a unit. Either A is a unit or B is a unit. There is no other choice. But if you are in a PID, then this definitely implies that if you are in a PID, then the converse is also true. Okay. In a PID, the converse is also true. That is, if it is irreducible implies prime. How do you show? A similar kind of proof. Let P be an irreducible element. Let P inside R be an irreducible element. If P is an irreducible element, so in a P, okay, so suppose P inside R be an irreducible element. So what you can say more? Be an irreducible element. My claim is P is prime. P is prime. In other words, it is enough to show The ideal generated by P is capital P is prime ideal. If I can show this, then I am done. Then I will be done, right? So let M equals to ideal generated by M be any ideal that contains P. That means the ideal generated by P is contained in ideal generated by M. So you know this P is an element of the ideal generated by M. This implies that P equal to some MR for some R. But P is irreducible. This implies that M is a unit or R is a unit. If M is a unit, then your M, which is actually generated by M, this is actually R. If R is a unit, this implies that M equals to P R inverse, which is actually ideal generated by P. This implies that this ideal generated by M is contained in ideal generated by P. This implies that the ideal is M equals to P. Okay, so this implies that ideal generated by P is a maximal ideal. Is a maximal ideal. This implies that this is prime ideal. But every maximal ideal is prime. This implies that this P is a prime element. Okay. So this is a prime ideal. So what else I can do? Let me just see what more I can do. So I think there will be something called UFDs, unique factorization domain, but I will do it in the next lecture. But something is remaining in here also. So do you know, if you have any PID, then it will also it will contain a maximal ideal. Let me finish this lecture by defining this small thing. Then after that I will define UFDs. Okay. So I think I should have to define something is called. Okay, let me give some 10 to 15 minutes more. So if you have any PID, so do you think that there is a maximal ideal? The PID that will contain a maximal ideal. You know what is maximal ideal? The definition of maximal ideal, you know, right? So you know, in a field you have only two ideal. That is, the zero is only the maximal ideal. Okay. So if R is a field, then your zero is the prime ideal, right? So what you can say if you are in a PID? Let me write a proposition over here. Then every PID contains a maximal ideal. What is it? Suppose the case 1 R be a PID and R is a field, FIELD, field. This implies that zero is only maximal ideal, and zero is already contained in any of the ideal, right? So there is nothing to prove. Suppose case 2 R is a PID but not a field. R is a PID but not a field. But R is a PID but not a field. How can we deal with that? So I will use something called as John's lemma. Okay, before that I will define the partial order over that. So what is a John's lemma? You know what is a John's lemma says? What is John's lemma? That if you have any partial order, that and every chain has an upper bound in that partial order, then it will contain a maximal ideal, right? No, sorry, it will contain a maximal element. So that element that will be the desired maximal ideal over here. So you know what is the John's lemma, right? I am assuming that at least you know the John's lemma axiom of choice. So I'm not going to define what is John's lemma, and you know that very well, John's lemma, because you are in a vector space. When you are linear algebra, you already know that every vector space has a basis. So for that you have also need John's lemma. For the proof you also need the John's lemma, right? So I'm assuming that you already know John's lemma. After that, suppose so R is a PID but not a field. Suppose A1 be an element of R. A1 be an element of R, non-zero. A1 is non-zero, right? So I am defining this I1 is ideal generated by A1. If I1 is maximal, then I am done. Suppose not. If not, then there exists an ideal. This implies there exists an ideal I2, such that this I1 is properly contained in I2 is properly contained in R, right? Since we are in a PID, so suppose we are in a PID, then I2 is ideal generated by suppose A2. Since you are in a PID, roughly I am doing the proof. You are in a PID, so this. If not, so there exists an ideal I3. If this is maximal, then done. If not, this implies there exists an I3, such that this I1 is properly contained in I2, is properly contained in I3, is properly contained in R. Okay. So if I3 will be generated by some single element A3. If this is maximal, then done. If not, so there will be keep continuing this. I will have a chain of ideal, right? Continuing this, I will have a chain of ideal. I will have a chain of ideals, that I1 is properly contained in I2, is properly contained in I3, is properly contained in I4, and it is properly contained in R. I have a properly chain of ideal, and I am defining a partial order over here. Define a partial order I1 is related to I2, or I1 or I is contained I is related to Ij if and only if II is a subset of properly contained in or properly is Ij. So you can verify this is a poset, that is, it is reflexive, antisymmetric and transitive. This is going to be a poset, partially ordered set. And if you have this poset, so what you have more than this ideal, the collection of ideal I varying over some indexing set lambda, is a poset, partially ordered set. So we'll use John's lemma. Use John's lemma. Use John's lemma. That means if every chain in a poset P has upper bound, every chain in a poset, that means partially poset P has an upper bound in that poset P, then it has a maximal element. Then it has a maximal element. So I have a chain of ideal I1 is contained in I2, sorry, I2 is contained in dot contained in R. So this is a chain of ideal. And what is the upper bound? Upper bound is union of I equals to 1 to infinity II. Okay, this is an upper bound. That you can every chain, you take every chain, that it will be an upper bound. So why this is a proper ideal? Why proper? You can check why. Because if it is not proper, then it will be, because this is an ascending chain of ideal, right? This is an ascending chain of ideal. So it has to become stationary after some stage, because the concept of Noetherian will come after you will learn some basic ring theory. After rings on modules or in commutative algebra, it will come the concept of Noetherian. So it will say that every ideal ascending chain should be stationary after some finite stage. But here it says that this is an upper bound, and this upper bound is lying inside this poset P. Why? Because this is a proper ideal. Because if it is not proper, then it will be something, because it is contained in I1, I2 is contained in some IK. If this IK is inside R, then it will not become a proper ideal. That will not be a maximal ideal, right? So it has a maximal element. Okay, so it has a maximal element. So this upper bound. So by John's lemma, it has a maximal element. And this maximal element is our maximal ideal, and this maximal element is our maximal ideal. That's the idea behind the proof. Okay, so that much. And what else is needed? So this is a maximal ideal. So what else should let me remind what we need to show, what I can define something. So what do you think if you have question this Rx by ideal generated by x square plus 1, what it will be, what the structure will be? And we'll discuss, and this will be isomorphic to a field. And which field? And this will be isomorphic to the field C. See, this R is a field. This implies that this Rx is a is Euclidean domain. This implies that Rx is a PID. Every Euclidean domain is a principal ideal domain. So you just need to check this x square plus 1 is prime or irreducible. This ideal generated by x square plus 1. So this element is prime or irreducible. What do you think? This element is prime or irreducible. What do you think? So it is irreducible. If it is irreducible, you are in a PID. So if either it is show you irreducible or prime, they both are same. That means in a PID you know that every irreducible is prime or every prime is irreducible. There is no change. Either you show this is prime or irreducible, or you show irreducible or prime. That's up to you. So what do you think? Is it irreducible? Suppose this x square plus 1 can be written as sum. So see, it is irreducible, then you can have to sum x minus alpha, x minus beta, right? See, this x square plus 1 has no 0 in R, but if you want to write in terms of, see, it has no 0 in R, but this x minus alpha, x plus alpha has 0 in R, because alpha beta should be a member of R na. So one of them must have to be constant, actually one of them. If it is reducible, that this polynomial is not irreducible, okay? So if it is irreducible, x minus, but this element has no root in R, but this, if you can write this, then this implies that this has root in R, but which cannot possible. So one of them has to be constant polynomial. This implies that this x square plus 1 is irreducible. This implies that x square plus 1 is prime. If it is prime, then it is maximal. This implies maximal. If it is maximal, then Rx by ideal generated by x square plus 1 is a field. Okay, so what is the field? Field is actually C. How do you define this? C, I am giving you the hint. You define R of I. R of I is actually, this is also known as C. If you take any polynomial px, you go it some p of I, then the kernel will be, suppose you take it f, kernel of f will be ideal generated by x square plus 1, and this will imply that by use fast isomorphism, and this is going to be an onto ring homomorphism. Okay, onto ring homomorphism. So that's the proof. Okay, that's for today. So we'll meet in the next lecture, and next 2 or 3 lectures I will finish ring theory. The entire ring theory I will finish. Okay, thanks for watching.